Introducing our next presenter, Vangelis Kaperdas. Vangelis is a Customer Service Engineering Director at the Beta team in Greece. He works on the field spanning all around CFD applications for 25 years. He will present us today how Fidelity CFD is now integrated within the ANSA platform to provide a seamless environment from CAD to post-processing with Meta, leveraging a GPU-powered CFD solution. Again.
Thank you, Michael. Good afternoon, ladies and gentlemen. I'm going to start my talk with a phrase that sounds a bit of a cliche, but in fact, I'm very excited to be here. You see, I don't remember myself ever giving a CFD presentation in the main amphitheater of our conference. You see, with all the latest developments, CFD has taken a big push, and it's now under the spotlight. So, as we said in the morning, it's been over a year since the acquisition of Beta CA Systems by Cadence. I'll be frank, it had been, you know, a challenging period, for sure. We had to adapt, learn new things, new communication platforms, new procedures, and we had to find our equilibrium, our stable equilibrium, within a much bigger family. Having said that, I'm very pleased to say that I'm also excited to have many new colleagues that are passionate about CFD like we are. And together, over the past year, we have accomplished some great stuff, which I'm about to show you. So moving on, this is the workflow that we designed by combining the best of both worlds, right? So we took whatever was best in every company, we merged it to form in one streamlined, fast, and complete CFD workflow for external aerodynamics. So you will see here at the top, starting with ANSA, of course. We start with the geometry input, the CATIA translation. Then we do a lot of filtering out of parts, what to keep, what to merge. That's a big part of the process. Then we move on to the wet surface extraction to isolate the wetted surfaces. Then we move on to the now integrated inside the ANSA environment Fidelity Auto Seal, a truly amazing function that can create a watertight model in a few minutes. Then moving again in ANSA for volume meshing to create a high-quality volume mesh. And also setting up the whole CFD simulation, right? Setting up the solver numerics, the boundary conditions, the materials, everything, so that we can output a ready-to-run case for the new Fidelity CFD solver, the powerful GPU solver that can do all runs and DS simulations for the automotive industry. And finally, we can post-process all this thing in Meta, fully automatically, thereby closing the whole loop of the process. I would like to guide you in detail throughout all these steps with a real data set, not a dry-wire model, right? So we were offered the Audi e-tron 55 geometry in CATIA format, provided by Caresoft. We used the latest versions of our software, ANSA 2025.1, Fidelity CFD 2025, and Meta 2025. These are the versions that are about to be released very soon and be available to you. For hardware, we used very nice, for pre and post processing, an AMD Threadripper workstation with 256 gigabytes. And for CFD, we used 16 GPUs NVIDIA A100. Let's start with the CAD data import. We're talking about a serious data set that it consisted of almost 7,000 CAD parts, 21 sub-assemblies, a total of 23 gigabytes of data, right, that we had to work with. Some details, this means, this translates to 7 million faces, 12,000 PIDs, and 29,000 unconnected components, right? And this was translated using ANSA, using 20 ANSA parallel processes, and merged in the end into one in something like an hour, right? And the resulting ANSA file was 24 gigabytes. Again, just to point out, the size of the data that we had to deal with. The first thing we need to do after translating all this data is to somehow discover the model, right? We want, first of all, to filter out unnecessary components. This, of course, speeds up all the subsequent steps, like the geometry tessellation, the extraction of wetted surfaces, leak closure, volume meshing. Everything is affected by what you feed in, right? So the less data you provide, the faster you will get the result. And of course, it reduces the file size. Then we need to defeature some unnecessary details for the CFD simulation. And we somehow need to turn this, 10,000 PIDs into a meaningful number of PIDs for the CFD analysis, right? So, because you need to apply boundary conditions and post-process this thing. It has to be practical. So, how do you navigate through a model with 30,000 components and 12,000 PIDs, right? Okay, you can open the property list. It will list 12,000 PIDs. That's just a list of names, sometimes incomprehensible. You actually need a map to navigate through a data set like that, right? And what's good is in ANSA, we don't just have a map. We actually have, I would call it a GPS, the model browser, right? Which is a tool that can help you navigate through the model, either in thumbnail view icon or in tree view. Right? So you can see all the subassemblies exactly as they were designed in CATIA or any other CAD system. And you can filter out what you want and what you don't want, right to the last bolt or washer. So using, first of all, an overview of the model browser, you can quickly deduce that some subassemblies are useless for our external aerodynamics analysis, right? And we can just throw this out. In fact, if we knew this in advance, we wouldn't have translated this data, right? It would have been more reasonable to only translate the data that you need. So the translation time would be even less. Then you're still left with many components. We use the function isolate connectivity groups. This can run in a few seconds. You can have a list of all the unconnected components. You can sort by volume. And you can find and filter out anything that is smaller than, say, 5 cubic centimeters, right? Again, this is a personal preference, but you can see that this model consists of spot welds, washers, nuts and bolts that you can remove for the CFD simulation. And this, removes completely 18,000 components. Then you do need to do some defeaturing. For example, on the tires, we don't want to keep the tire threads. And we use a function called isolate similar groups, which can detect similar patterns, and you can select and delete these components, right? So you can filter them out, remove them, and then use fill hole and have a nice clean tire. Some other defeaturing that we can do in mass, using, again, scripts if needed, is to detect, openings and holes like these. Sorry, And this is done with a function called fill holes. It's a simple thing to do. You isolate feature line holes or free edge holes, and you can close them. For simple holes like that, there is fill hole. For all the rest, there is autoseal. Now moving on to merging PIDs. Again, we're still trying to battle ourselves to thousands of PIDs, but again, we can use the model browser and, for example, quickly isolate the frames. They consist of, hundreds of PIDs, and we can very easily merge them either, by selected, by name, by color. There's functionality a lot to merge PIDs into one PID. Now let's move on to wetted surface extraction. Here we have our model browser, remember, the basic tool to navigate in ANSA. You can take each subassembly and run the function called isolate visibility groups, which scans around the model and sees whatever is visible externally and can mark what is visible and what is not visible, thereby isolating all the interior components. And we can remove them. We can apply the same to the whole vehicle in the end, right? Helping, of course, the algorithm by removing some things like the wheels and the front grille so that we can see inside. Probably the bonnet as well. This should have been removed. And then you can automatically identify what's inside and not seen externally, which we can remove as well. Again, a lot of stuff that can be removed. So we start from 7 million faces, and we end up with 2.4, right? That's a big improvement, and from 30,000 components to just 6,000 components. So this is nice now to send to, oh, sorry. Apart from that, you need also to do some geometrical constructions to create a valid CFD model. First of all, of course, you need to create a domain. We have a function to do that in the latest ANSA version, very easy to use. You define your domain with the size. You need, of course, to replace the detailed geometry of the radiator and condenser using simple porous media. Again, a function that can select a group of faces and replace them with a square parallelogram. Create tire plinths at the tire contact patches, another specific function. Here we create a plinth of almost 1 millimeter size, very small one, to improve the volume mesh in that area. Then we need to create, of course, the MRF zones in the wheels. Here you can imagine it gets a bit complicated because there are a lot of details. So you need to create this MRF zone that will, of course, pass through tight gaps, especially in the disc brake. And also you need to ensure that it intersects normally whenever it meets a wall, right? So that you can grow layers easily, with good quality as well. Again, there is a dedicated function for that. It's called rotating interface. So we did this for the front wheels to create this green area, and also for the rear wheels. And once we did that, we symmetry copy for the other two. Finally, there is also another MRF zone in the cooling fan, right? And again, a very tight gap here to pass through and ensure that you can generate a volume mesh, grow a few layers, and within very narrow tolerances. Then, yes, this is just geometry. It's not meshed, right? So in order to proceed from here, we need to tessellate it, right? And to do that, we use batch meshing and the STL meshing approach. And this is done in something like half an hour to create 64 million triangles. And now we have a tessellated representation, which we will send to AutoSeal. As you see here, AutoSeal is integrated in the ANSA GUI, here at the top. And it's very easy to use. There is a window where you need to specify the leak points, the so-called dry points as well. If you go into detail, here it's easy. You just pick points from the interface. You usually have a cutting plane. You scan through the car, and then you pick points that you know that the flow should not go into. You can also help by also providing wet points, seed points, right? Because in some areas, you know that you want the flow to go in, like, for example, here. To avoid AutoSeal closing the grills, because there's a very narrow gap, you can put some extra wet points inside. And then you specify a few things like, yes, that's an extra feature. Whenever you have some components that are still, in the assembly, they're not fully internal, but they're very close to internal. You can feed them into AutoSeal as additional dry surfaces, right? And this can help AutoSeal close the gaps just on the outside of the volume, right, to avoid going inside gaps. You also specify, of course, the leak length, 1 millimeter, and it's recommended that you also specify some limitations on RAM and CPU usage, right, to avoid overflowing the computer. Still, I would say the algorithm is very impressive because it can create 1,500 closing patches in 37 minutes, right? So this task would have taken days to do manually, and it's done here very quickly and to a very good quality. So if you see here these gaps, typical gaps in an automotive geometry, these are sealed automatically by AutoSeal. The surfaces are smooth as butter, and then ANSA can do an extra post-processing to automatically assign them to the neighboring PIDs, thereby making these surfaces invisible, right? So you just don't see them in the model. We don't want to add new properties. We want to stick with what we have already. Now, having done all this, we have a watertight model. We can go to volume meshing, right? For volume meshing, we want to specify some sizing fields. We have the size field entity. This can consist of size boxes and additional very useful rules like surface offset, sweep, and so on. And you can get a very nice preview of the size distribution of your mesh, right? So you know where things will be refined and you know what the length will be in every location. And after having specified the size fields, you need to go to Hextream, right? For this, you know, for automotive geometries, which are always very complicated, we prefer to use Hextream, the volume to surface algorithm, an octree algorithm, which has the advantage that it does not require a watertight geometry, right? As long as there are no leaks, you will get a high-quality mesh. So what we do, we have our PIDs. We have merged them into a reasonable value, like I think something like 100 PIDs. And we can now somehow put these PIDs into Hextream and feed them into different so-called areas, right? Every area has different meshing specifications. And at the bottom, we specify the volumes that we want to mesh, right? The main volume, the MRF zones, the porous media, and so on. Here we specified with seed points, but we can do it with name filters as well. So if you see now the color coding in Hextream mode, you can see the different areas. So every color has a different meshing specification, you know, a smaller element length, a better proximity refinement for the grill, for example, to ensure that all these gaps are maintained. Before actually running Hextream, you can ask it for a preview of the volume mesh that will be generated, which is something very useful because, in fact, you can see the mesh distribution that you will get before actually doing the mesh. You will see the identified volumes that have been identified by Hextream, an estimation of the total cell count for every one, so that you can see that, you know, it's going to go well. You haven't asked for 1 billion elements or something. And you can scan in different directions, right, in every direction. Here you can see, for example, the identified MRF volumes in the wheel and the disc brake and the refinement around the wheel. If you're happy with that, you can actually proceed with the volume meshing step to get a mesh of 213 million cells. I will give you some overview of the mesh, how it looks. You can see all the internals in the underhood have been meshed. Nothing has leaked inside. And you can see a very nice distribution of the mesh with very nice layers capturing in all surfaces. Here inside the porous media and the MRF fan, you can see the mesh is conformal, right? Everything is connected with conformal mesh. The bottom here, you can see details like, for example, the rear windscreen wiper, the spoiler, everything has been captured to a very good, very high detail. And again, remember, this is just 213 million cells, right, for a car, representing every single detail. Also here, you can see, for example, the conformal mesh between the MRF zone and inside the disc brake as well. The tire plinth, remember, this is just 1 millimeter, and the gap is very well captured and resolved. To actually see the level of detail capturing of the algorithm, it's better to see the actual surface mesh and not the volume mesh. So have in mind that the surface mesh varies from 0.6 millimeters at the tire plinth to a maximum of just almost 7 millimeters. And you can see the level of detail that we have captured with Hextream, right? Everything looks very crisp. All the features, curvatures have been resolved. even to, the small antenna at the top. The front wheel deflectors, all the details are very well captured. The wheel. Here going inside, these are the two porous media, right? And you can see a front grille just upstream of the condenser to protect it from, I imagine, some debris. These gaps are very small. And the fan, and even if we zoom into these flaps around the fan shroud, you can see the level of detail we've captured. And again, remember, this is 213 million cells, right? It's not something huge. The mesh looks good. It also has to be good. We check it for quality criteria. We use the native Fidelity CFD quality criteria definitions, and we get very good quality metrics for them. So it passes all the checks. Having completed the volume mesh, we move on to actually setting up the Fidelity CFD simulation inside the ANSA environment. Actually, after creating the volume mesh in Hextreme, it's always recommended that you do a boundary conditions check with the function that we have. This function will identify if there is a problem with the boundary condition types, right? If, for example, you have an interior boundary on the outside, or if you have a wall boundary that connects to more than one fluid region, it will tell you, it will identify automatically any problems and will suggest fixes, automatic fixes that you can apply until everything is green, right? This step may create some extra PIDs, right? So you can separate the wheel to wheel fluid and wheel fluid MRF, right? If it was one PID only. And again, something fully automated. Okay, now we can go on to the actual setup of the Fidelity CFD case. Again, a button here inside ANSA. We have created this nice, simple to use setup window where you start with the solver setup, the simulation setup, the solver controls, number of iterations, time steps, and so on. Then we move on to materials. Here, okay, of course, there's only one material. We move on to the regions. We have all the regions. We can see which are the boundaries attached to these regions. And we can apply the rotating conditions for the wheel. Here there is a very useful option to automatically calculate the rotation axis and display it, right? So you can ask ANSA to find the rotation axis. So you only have to fill in the actual rotational speed. And finally, you move on to the output request. Sorry, I think I'm missing a slide where we also set up the boundary conditions, right? For the inlet, the translational road velocity, and so on. Here you output you specify the output request, right? Whatever you want to get from the solver, the field variables, the drag coefficient, and so on. Again, here functionality to automatically calculate the projected area so that you don't have to go elsewhere. And, this is the specification of the rotating walls, right? The tires are also rotating, so you need to impose this. Again, with the automatic calculation of the rotation axis. You can visualize your model into the so-called boundary conditions type view mode so that you can recognize quickly white is wall, green is interior, just some color codes like that. And we have also added a mode where you can specify, you can visualize the velocity magnitude that you have imposed, right? So you can see and confirm that the wheels are rotating correctly, the road is moving, and so on. So having created the mesh, having specified the case setup and all the details, you can simply go to File Output and output the Fidelity CFD case, which consists of an IMP file and the mesh. Note also that we have some very useful functionality from this window called, where we can actually sync an IMP file. We can take this file and send it to another model, or we can read an IMP file from another model and map the whole case setup to our new mesh, right? So that we don't have to go and set up again everything. Now let's move on to the actual CFD solver, right? It's called Fidelity CFD, as you've heard many times today. It has quite differentiating technology. It has a coupled solver that produces fast, steady-state convergence. It has also a segregated solver for fast transient simulations. It has novel technology that provides stability and robustness. It's an all-speed solver, whether the flow is incompressible, compressible, supersonic. The solver can handle all. And it's specialized for external automotive applications. It's a code that is written once for both CPU and GPU, right? And it has many capabilities for fluid modeling, physics, turbulence models, and so on. Its characteristic, you know, is the fast and robust convergence, right? So usually you get a solution within the first couple of hundreds of iterations, which is very impressive. So in this case, we set up this scenario in ANSA, right? So you see the boundary conditions, 50 meters per second inlet velocity, steady-state simulation, k omega SST, with extended wall functions, and then we have the specifications of the MRF zones, the porous media, and so on. And we actually got a solution on 16 GPUs. Actually, the solution converged in the first 100 iterations, right? But we proceeded with 100 more just to filter the average, right? Again, this is a mesh of 230 million cells. If it were run on CPU mode, you see on 480 CPUs, it would have taken 3 hours, whereas now it only took half an hour, right? So that's a speed up of, I think, something like 200. Actually, the solver can detect on its own convergence, not based on residuals, of course, but actually on the statistical error of the time signal of the drag and lift coefficient, right? So it can do automatically all the statistics and evaluate the amplitude of the oscillation, the uncertainty, and so on. Finally, yes, we can go to meta. Again, we have the mesh of 230 million cells. We can read this in something like a minute, read 3 scalar and 1 vector results in a minute and a half. And then we can generate automatically a report which consists of 320 images in something like 10 minutes, right? And this requires only 75 gigabytes of RAM. We can get all the nice plots that you can imagine, like, you know, cutting planes of velocity, leak visualization on cut planes, leak visualization on surfaces, ISO surfaces, all that you need to do your post-processing, animation of cut planes. And of course, you don't have to do it. Meta will do it on its own, right? Based on a journal, a session file or a script. It will create a PDF or a PPTX report automatically, right? You don't have to do anything. Now, let's see something about the metrics, right? Because that was the whole process. I tried to list here an estimation of, you know, the effort that takes place, both for manual and automatic work. I would have to say that, you know, this was a case where I was given, you know, a new set of data I wasn't familiar with. So you will see a lot of time spent in the so-called model discovery, right? Figure out what is needed, what can be thrown away, what should be merged, what should be defeatured. In an ideal life scenario, these things could be automated if there were some, you know, Excel sheets that automate this. You know, the manufacturer, the OEM knows that these components can be thrown, these can be merged, these can be removed, and so on. And so in total, I would say something like 24 hours, right? From CAD to the actual CFD results. You can see that the actual solution is just a fraction of it, right? It's half an hour, which is nothing. I would need to say, of course, what if we were to do a model update, right? This was the first simulation. Now we want to change, you know, the rear spoiler or the mirror and things like that. Things here would be much faster, right? We wouldn't have to go through all this effort to set up the model. So I would say that, you know, if you want to do a design update, you would only need something like 4 hours to simply replace the new geometry. And of course, you may notice that, there's the bottleneck, extreme volume meshing, right? Just to say something on its side, that you have in mind that Hextreme does not require a watertight surface, right? So you don't have to do a surface wrapping and then move on to volume meshing. You simply do the volume meshing directly. Also, is capable of capturing every bit of detail with a relatively low cell count, thereby making a smaller mesh that will resolve all the details and be solved faster. And as always at Beta, we always focus at the beginning on high quality, right? So our target for Hextreme has always been high quality mesh. And of course now, having achieved that, we can move on to improving the speed, right? So bear with us and we will work on that as well. So at the end of the day, I was asked by my manager, your presentation should answer one simple question. Why go for ANSA, Fidelity, CFD, and Meta, right? So I will try to summarize here, and I will say that, ANSA has the most complete pre-processing portfolio for CFD, right? It has all the powerful geometry handling and management tools that you need to handle such kind of data. It has high-quality automated meshing with all meshing workflows, right? Whether that's volume to surface, surface to volume, structured, anything. And it also has extra tools like morphing, connection to DM systems, and much more. It supports Fidelity CFD from the same environment. And of course, you already have it. Make the most of your ANSA license. For Fidelity CFD, for sure, I cannot, not see the unprecedented speed with its GPU technology, fast convergence of the couple solver, get your result in half an hour, which is very impressive. And finally, for Meta, the best software, you don't even have to see it. It will run automatically and will create your PDF report to examine the results. Of course, in my presentations, I always want to mention the support, right? Imagine you have all these tools under one umbrella with the same level of support that you've been accustomed to for a long period of time working with us. This concludes my presentation. I think I took on purpose most of my time to avoid any difficult questions, but still, since we have a break, thank you.